Right, okay. So this session is about summer astronomy. I saw on Twitter one of my friends from down south. They get pretty dark nights all the way through the summer. They live on the south coast, so it really makes a difference being like a few hundred miles north. You really do not get dark skies in the middle of the night, especially kind of like the few weeks around the solstice in June. So this is kind of with all of that in mind. What can you do if you're determined to do astronomy during these months? So summer astronomy. As usual, if you've got questions, please type them into the chat. I'll either notice them or I'll pick them up at the end. This is what we're going to go through. I've picked a few kind of events and things that are kind of unique to this year, as well as the usual noctilucent cloud and deep sky stuff. So I'm basically going to go through that. There might be other things that we end up talking about. Who knows? Let's see. So I'm going to start with an event that you can see tonight and tomorrow night and the night after if it's clear. Okay. So I'm going to start with Mercury and Venus. So this is the view tomorrow night, looking towards the northwest at 20 past 10. So this is roughly, it'll be about an hour, maybe a little bit later after sunset. Okay, so the sky's still quite bright. And what we have here is a conjunction. Okay, so this is an alignment of Mercury and Venus in the night sky. So Mars is there as well, but you won't see Mars until it gets a little bit darker. So Mercury and Venus appear very close together in the sky. If we just zoom in a little bit and take a closer look, you'll see there's a huge brightness difference between Mercury and Venus, okay? The difference caused by the fact that Venus is a much bigger planet, surrounded by very highly reflective atmosphere of thick clouds. Mercury, a dark, small planet, as dark as the moon, and also much further away. Venus is much further away, but it compensates by being bigger. So Mercury, you'll probably need binoculars to see it, but it's sitting right next to Venus in the sky. So if you can see Venus and you've got good eyesight, and maybe just before they both set, you might actually pick up Mercury next to it as well. This is the binocular view. So I'm just looking for my pen to kind of draw on the screen a little bit. So they look really close together in the sky. I'm not exactly sure how far apart they are. I suspect they're closer than the width of the full moon. This is obviously an illusion. In reality, Venus is on the far side of its orbit. It shows an almost full phase. Mercury is much closer to us. It's actually swinging around to come between us and the sun, more or less, and through a telescope it shows a crescent phase at the moment. So if you want to kind of like picture what's going on here, if you've got your solar system with the sun in the middle, okay, there's the sun, okay, you've got Mercury, Venus, and the Earth, okay, so the Earth's over here, and right now Mercury is kind of there. Okay, it's kind of like moving that way around its orbit. So it'll very soon be between us and the sun, whereas Venus is round the back like that. So Venus is over there. So it's behind the sun, being more fully illuminated. It's just to give you an idea of the millions of miles that are actually still between Mercury and Venus. So Venus is bigger, more reflective. It looks much brighter in the sky, despite the fact that Mercury is nearer. And also Mercury shows a crescent. If you were to zoom in on Venus, it looks like that, almost full. If you were to zoom in on Mercury in a telescope, it kind of looks like that, a really narrow crescent. So there's not much there to reflect light our way, which is why it isn't so bright at the moment. Okay, so that's, you could see that tonight. Tomorrow night will be when they're at their nearest together, and tomorrow, the night after that, they'll be a little bit further apart. Mercury will drop in towards the sun. Venus is going to be hanging around for quite a bit longer. So this is a special kind of diagram to show you roughly where Venus will be after sunset. So roughly 45 minutes to an hour after sunset, you can see that it's kind of like around here at the moment. It's It's a few degrees above the horizon in the northwest an hour after sunset. And actually, as you go through the next few months, it doesn't improve. It's actually going to drop down towards the horizon. So it's going to be harder to see until you get into the latter stages of the year. So when you get into the autumn in October, it begins to climb a bit higher into the sky until around about December, we start to get a slightly better view. So this whole kind of apparition is very different to how it was in the previous evening apparition, when it was very high in the sky, visible for hours and hours after sunset. So it's all to do with like the tilt of the Earth's axis to its orbit. So for example, we're getting a really poor view of it this year, but people in the southern hemisphere or nearer the equator are getting a really special view of it. Okay, so there you go. Conjunction of Mercury and Venus. Right, now, one of the things I really wanted to tell people about are clouds, okay? We love clouds, don't we? Well, these are special clouds, obviously. I wouldn't be talking about them with a smile on my face otherwise. These are noctilucent clouds. So this is a picture of them. Do you know on your Zoom app, can you find a thumbs up symbol? Give me a thumbs up if you've seen these before, if you're fairly certain that you've seen noctilucent clouds. I'm going to try and look through everybody. Give me, yeah, some of you are giving me a literal thumbs up that I can see, because 14 months into using Zoom, you're not quite sure where the thumb in is on Zoom at the moment. Yep. Okay, there we go. Okay, something in the chat. Thumbs up there. Thanks, Ian. Thumbs up from literally spelling the word thumb up from Derek. Thank you. Yeah, so these are noctilucent clouds, night shining clouds. This picture was taken a few years ago. You might recognize the silhouette of Warkworth Castle there. So I was looking towards the north. This is 1 a.m. more or less. So this is midnight, taking into account it's British summertime. This is the middle of the night. So it's not quite dark, but it's pretty dark. And those clouds are shining very, very brightly. So normal clouds that you can kind of see, you know, back here, down there, those are normal clouds and they're silhouetted because they're in darkness. But these ones are shining very brightly. And that's what I want to talk to you about. This is noctilucent cloud season. So how do you see them? How do you recognize them? Why are they special? So in this kind of cartoon at the top of the page here, I've tried to illustrate what's going on with them and why they're a little bit unusual. So we kind of like looking at where you are, which is over here. You're the observer and it's nighttime. Okay, so you're in the night. You know, it's nighttime, but if you were to travel north this direction, obviously you go in towards the Arctic Circle and it's daytime again, land of the midnight sun and all that. Okay, so if you go very, you know, much further north than Scotland, a few hundred miles, you'll be into daylight again. So over here, the sun is shining. Okay, so clearly the clouds nearby us, you know, within like 10, 20 miles of us, they're in darkness as well because they're not high enough in the sky. You could imagine climbing up here or, you know, sending a satellite up there and eventually it would hit sunlight. You'd go high enough to see satellites, okay? But if you go far enough north, there are some clouds and these are the clouds I'm talking about. So these are very high, but they're also very far north of here usually. And they're in full sunlight. So if you were standing on the ground here, okay, looking at them, I don't think you'd see them because daylight would completely overwhelm them. You just wouldn't see them in broad daylight. But for us, we're in darkness, so we've got a dark sky, and we're looking at these things which are fully illuminated by sunlight. So they turn out to be pretty impressive clouds at night. Now, there's a definite noctilucent cloud season, and it's started. The first noctilucent clouds have been spotted. I think from Germany, they were visible, very tenuous things, not very substantial at the moment. But from about the middle of May to the middle of August every year, these clouds form around the poles of our planets, okay? Around the North Pole between mid-May and mid-August and mid-November to mid-February in the Southern Hemisphere. So there's a very limited region of visibility. If you're too far north, it's daylight and you can't see them. If you're too far south, it's dark, but you're too far away from the clouds to see them. Okay, so there's a definite kind of window between about 50 to 70 degrees north where you're in pole position to see these things. So Northumberland is in the perfect place, 55 degrees north. We're absolutely right in the perfect place to see these things. Now the sky has to get dark enough, which means the sun has to be far enough below the horizon to see them. So for us in Northumberland, it's about 2 hours after sunset is when the sky gets dark enough. When it's reported on like websites like Space Weather, they're usually talking about kind of like people in the US. And for them, the sky gets dark pretty quick. So they're visible like 45 minutes to an hour. Here, you just won't. You won't see them till like after 11:30, getting on for 12 a.m. Okay. So you've got to be prepared to wait up to see them. Okay, this is a map taken from a scientific publication, which essentially shows the regions where they're visible. Okay, so these are the perfect places to see noctilucent clouds. It also happens to be nice places to see the aurora as well. So there's another kind of shaded band here and at the bottom. And this, if you were to kind of like visualize it on the sphere of the Earth, would be an oval where the aurora takes place around the poles. So this is us. We're right in the middle of the perfect place to see these things. And if you're in the southern hemisphere, not surprisingly, they're less well observed because along this stretch of the region, there's very little land. Okay, so maybe like the Falklands or the southern tip of Chile, Argentina. Occasionally they extend further north and south of those regions. So people do get to see them from more extreme latitudes, especially these days. So I'll talk about that shortly. Okay, so that's where they form. Now, I think it would be helpful to just keep showing pictures at various stages, okay? They're unlike any clouds you've ever seen. I think once you've seen them, you know you're looking at something unusual. This was a particularly strong display about 7 years ago, and it was over the River Coquet. I say over the River Coquet. These clouds are like 400-500 miles away. They're very far north of here. So they're not really over Warkworth or even over northern Scotland, okay? So they're very, very far away. They're very high in the sky, which is why we're able to see them from such great distances. Yeah. Now, these are a recently discovered meteorological phenomenon, okay? Now, we've known about like aurora observations all the way back through history. In this region, we've got like the Anglo-Saxon Chronicle, which goes back to like the 7th century AD. So we've got very good records of aurora and people watching the sky. There's nothing like this recorded in history until you get to the 19th century, okay? I'll leave you to ponder about what changed about the world in the 19th century, okay? But they were first seen in the 1880s and recorded in the prestigious journal Nature. Thomas Backhouse, who I'll tell you a little bit about in a minute, really publicized them in this country, got people out looking at them. So he made lots of observations in the middle of the 1880s. A German astronomer, Otto Jesse, began to observe them after that into the 20th century. I'll mention Backhouse because he's a local man, born in Sunderland, had an observatory there, a proper professional amateur astronomer, okay? So he loved the subject, had an observatory, and he just made observations and reported them. So we've got him to thank for many of the earliest observations of noctilucent clouds. He also wrote about zodiacal light, which you can see from this part of the world in February and March in the evening sky, and October, November. Zodiacal light is all the dust in the solar system being illuminated by sunlight, and you can kind of see it at certain times of the year, shortly after sunrise, after sunset and before sunrise. The Gegenschein is again dust, and it's referred to as the counterglow, and it's kind of like if you've got the sun over here and you've got the Earth here, okay? And you've got like just everywhere dust particles just scattered, might be in the asteroid belt, could be over in this direction, okay? Everywhere, just everywhere, dust. If you look in this direction, in the direction of local midnight, what you get is light from the sun reflected straight back at the Earth. It's just, this dust is illuminated really brightly. And so when you look at, especially on like astronomy picture of the day where they've got pictures of the Milky Way, you quite often see the zodiacal light, which is sort of a cone of light extending from the horizon. And then in the middle of the picture, you'll have this extra patch of light called the Gegenschein, which is kind of all of this dust being illuminated fully. It's like a full moon kind of illumination, the way the moon is fully illuminated. Anyway, he observed that, variable stars, the aurora. He did all this from Sunderland, but I suspect it was slightly less light polluted back in the 19th century. So yeah, Thomas Backhouse. Now, when these things first began to appear, people wanted an explanation of why these new clouds were appearing. There were a couple of theories. One of them was that previous to the first observations, there was a massive volcanic eruption from Krakatoa on the other side of the world, and that pumped a lot of dust and sulfur dioxide into the atmosphere, and that created absolutely crazy bright sunrises and sunsets all around the world for years after the event. So people speculated maybe it's like the dust from this, which is the seed for the clouds, which are now forming, which everyone is now able to see. Other people thought maybe it's because like lots of people are just now out after sunset, looking at the evening sky, and therefore there's more people and therefore more of a chance of these clouds, which might have been there always, being noticed. So, you know, there was no real kind of like conclusive evidence either way about what noctilucent clouds were, or whether they'd just been missed until after the eruption of Krakatoa. I'll just check in the chat because I can see questions coming in. Yeah, okay, we'll come back to that, Ian. Yeah, so these spectacular sunrises and sunsets inspired one of the most famous paintings of the time, and you can see in the background there. I mean, you know, I'm not an artist, and I wouldn't even attempt to interpret a painting. Okay, but I can imagine like something new and spectacular suddenly appearing in the sky, feeding into a kind of panic that things are not quite right with the world. That's how I kind of like look at this. But anyway, this is written 10 years after Krakatoa, when these sunrises and sunsets were probably fresh in the memory. Now, noctilucent clouds, they appear in the summer months. They're a phenomenon of the summer months. Every year, there is a kind of variation in them, okay? So it's very difficult to get good kind of data on this, or historically it's been difficult. So you don't have that many people out looking and recording and counting the number of displays. But there is a variation. And if you look at the period of variation between kind of like peaks, you've got one in kind of like here, you know, roughly there. You've got another one here. What do you think that might be? What do you think might be causing that? Answers in the chat. So what do you think might be causing the variation in frequency? What else do you know about in astronomy that undergoes periodic variations like that? Yeah, okay. So, solar maximum and solar minimum. It looks like it might be correlated with that, but it's kind of interesting because it's not quite that. There seems to be perhaps a delay or a lag between the peaks. So this is the sunspot cycle, and you can see that in blue, you've got the number of nights where noctilucent clouds were seen, and also you've got alongside it in green the sunspot count. So the variation is there, but there's a delay. Okay, so I'm not quite sure why that's the case. It's not there. The period is the same, but it's offset. Now, noctilucent clouds are in a very difficult part of the Earth's atmosphere to study. I'll show you a picture of where they are in relation to everything shortly, but they're not high enough to be easily studied by satellites, and they're too high to be easily studied by aeroplanes and even kind of like small rockets sent up by universities from the ground. Okay, so they're in a kind of middle part of the atmosphere, which is traditionally very difficult to study. So if you want to sample what these clouds are made of, it has been difficult. This is a nice shot looking down at them from the International Space Station. So this is your cartoon of the sphere, okay? So for a sense of scale, if you've been noticing like aeroplanes and contrails today, look at where they are at around about the 10-kilometer, 6-mile mark, okay? So noctilucent clouds are up here, very, very high. They are the highest clouds in the atmosphere. They occur in a region called the mesosphere, which is above the stratosphere. And it's a region which is becoming increasingly studied because there are really unusual phenomena happening up there. Does anybody know what they might be? Those weird things in the atmosphere up there are a kind of lightning, which are called sprites. And they seem to be associated with thunderclouds, which are down here. So if you've got a big cumulonimbus cloud, quite often you get these sprites shooting up into the upper atmosphere, and they occur in the same region where meteors are to be found and your noctilucent clouds are to be found as well. So it's satellites orbit much higher. So the space station, for example, is around about 400 kilometers. So you can see we'd have to like double the height of the screen and then probably double it again until you're at the space station. So they're a very tricky place in the atmosphere to study. Now, the mesosphere is one of the driest parts of the atmosphere, much drier than like the driest desert on the Earth, okay? Virtually no water at all up there. And the water is down here. So how does it get from here up to all the way up to here? How do you transport water up there? At the top of the troposphere, there's a boundary called the tropopause, and water just can't get past there. You might get the occasional thunderstorm, which can punch up through it, and maybe that somehow enables like water vapor to be lifted up to those heights. But we don't think that the water which forms the noctilucent clouds up in the mesosphere comes from that source primarily. So there has to be another way for water to appear up there in order for these clouds to form. And the other thing is, what's the seed? What do they condense onto? What does this water vapor, when it appears, actually condense onto? And we didn't know what the answer was conclusively until about 10 years ago. It turns out that the seed onto which these things condense is meteor smoke. So as the Earth travels around the sun over the course of a year, it sweeps up around about 100,000 tons worth of meteor dust.
You had a busy day.
That stuff entering into the atmosphere. So the AIM mission, Aeronomy of Ice in the Mesosphere, is a NASA mission. It was launched in 2007. And this still continues to provide data from orbit of noctilucent clouds. So it's looking down on them, and it's kind of analyzing light passing through the clouds. And because of that, it's able to use spectroscopy and cameras to analyze the size of the dust particles which are contained in the clouds. Now, if you go onto spaceweather.com, you'll find down the left-hand side of the page the daily daisies. And if you look for, like at today's, it's not as extensive as this, but you'll see in the Northern Hemisphere map that they're starting to appear. So noctilucent cloud season has begun. The satellite goes around the Earth every 96 minutes. So in each picture, you can kind of see like a section here. So it's like the satellite flies over in that direction over the pole. And as it's doing that, the Earth is turning, okay? So the Earth turns, and the next time it flies over, it's flying over 90 minutes later over a different section of the Earth. So over 24 hours, it maps all of the noctilucent clouds, apart from the middle bit where it's daylight and it can't see those clouds there. Okay, so these are the daily daisies, and they're worth looking at. If you look at the picture, we're down here. Okay, it looks like we're nowhere near the clouds, but remember, we're in darkness. We're in the perfect place to see them. These things are so high, when you actually see them, these are the clouds you're looking at. They're so far north of the UK. It's incredible that you can see them. In recent years, scientists are coming to the opinion that noctilucent clouds are actually traces of climate change. Okay, so in the chat, one or two of you have mentioned the Industrial Revolution as a big kind of change in the Earth in the 19th century. So we've been putting out greenhouse gases, notably CO2, but also water vapor and also methane. And the mechanism by which the water arrives there is that methane can actually make it up to those layers of the atmosphere. And Derek would probably be the person to talk to about this, but you can in the action of ultraviolet light, methane can break down and produce with the stuff that's already in the atmosphere up there, water vapor. So that's where we think it might come from. So the water vapor is increasingly prevalent in the atmosphere because we've been putting out more and more methane since the 19th century. So although there's a variation, and I kind of alluded to the fact that every 10 years it does this. So every 10 years it does that. What you didn't see in the picture is that there's a longer trend where the noctilucent clouds are actually doing this. The frequency is kind of increasing. The number of clouds you see every year is increasing. I've been watching these things since the mid-80s, since before I even knew what they were. My bedroom, when I was a teenager, was like facing towards the north. So during the summer months, I would get great views of these really weird clouds. And there were like the occasional really bright display of these things, but nothing like there is now, where we've been able to see noctilucent clouds every year, and lots of nights, lots of clear nights have brought them. So my kind of like feeling is that these things are definitely increasing, and studies and more formal counts of the number of clouds and so on show that they are increasing as well. Now some pictures. Okay, so they look like that. They're just, as the sky gets darker, they get brighter. It's like the contrast increases between the cloud and the background. So when you see them, you might think they look like cirrus clouds. And sometimes you see cirrus clouds, and we occasionally get pictures of them posted in the Facebook group. People, saying, I've seen noctilucent clouds, and they're not, they're cirrus clouds. But when you see them, they get brighter as the sky gets darker. To take pictures of them, if you want to shoot them, you're shooting in twilight typically, so you can get away with like ISO 400 or maybe even less. You can take exposures of 1 second, 2 seconds, 3 seconds. You want to try and get wide field if possible, so you can capture like a nice foreground, I guess, as well. Or you can zoom in and capture some of the detail within them. Every year, those sort of 7 or 8 years, we've seen them. So I'll just keep showing you pictures so you get an idea of what they look like. So again, 2nd of July, 4 years ago, this is just outside my house, essentially, just across the road. And I mean, they're just spectacular. They're when you look at them with binoculars, they still look sharp. They're so far away, they still hold their definition when you're looking at them with like optical aid. If you look at a cloud like cirrus with binoculars, it begins to look fuzzy because it's nearer and it doesn't have the kind of the structure. It doesn't look as sharp because it's nearer to you. Again, just sky was, this is 2 years ago. This display was overhead. The noctilucent clouds are pushing further south every year, it seems. So this was overhead, and there was a cut-off point just kind of like over where we were, where they seemed to fade out, but I don't think they'd faded out. I think it was just that they weren't catching sunlight anymore, even that high up, because they were over the UK. So they probably extend, into Europe quite a way, with a really strong display these days. Zooming in a little bit, you just get this color is the natural color. I haven't kind of like adjusted it or anything. They look blue, silver, blue, just spectacular. And they move. while you're looking at them, they kind of like drift and move. And if you see time-lapse videos of these things, there are plenty of them on YouTube. Look incredible, just like waves rolling across the sky. So from a few years ago, I think the star in the picture there is probably Capella. I think that's Capella up there. And again, just different shapes, different whirls and loops. And in fact, astronomers can classify the different types of structures. You can report these to, like there's a UK Noctilucent cloud group where you can submit observations. So there aren't like that. You've got these distinct types in here, but sometimes they're mixed together. So you've got a veil where there's very little structure, but it looks like the sky's quite bright. You get these rolling bands with sharply defined features in them. You get billows and whirls as well, okay? And quite often you get different mixtures of them too, okay? So they're just incredible, incredible things to see. The only clouds I really like. There you go, 2017, kind of like out looking over Red Row Broom Hill towards the north. So this is a big wide field shot, and the sky above me is quite, you know, it's quite dark twilight, but in the north it was just really bright with these clouds, and you can see the color blue coming through as well. Okay, so that's it, Noctilucent clouds, be on the lookout for those. Right, does anybody want to ask anything? I'm just going to take a quick breath and have a quick drink of coffee. So, there's an eclipse coming. Now, from further north, this is going to be an annular eclipse. An annular eclipse looks like that, okay? An annular is where you've got a ring of sun around the moon. The moon's kind of like, as it goes, I like drawing pictures on here, but if you've got the Earth here, and this is the moon's orbit, okay? The moon's orbit kind of looks a bit like that if you look at it from above. So if the sun is kind of like over here, and the moon is here, you get a total eclipse because the moon's quite near to you and it completely blocks out the sun, okay? Now, if the sun happened to be over here and the moon was here, the moon's further away, so it doesn't cover the sun completely. So that would be an annular eclipse. The ratio is 5:4, okay? So for every 5 annular eclipses, you get 4 total eclipses, okay? But anyway, this is the June the 10th eclipse. So you can see that in the animation, the central bit, that dark splodge which moves rapidly across the Earth, you would have to be standing in that to see the annular eclipse. So that's basically the kind of the red band being traced out there, okay? So if you were lucky enough to be there, you'd see the annular eclipse. Now, obviously, we're down here, okay? So we're going to see a partial eclipse instead. So eclipses are quite rare from anywhere on Earth, okay, if you don't travel, but you're going to make the most of this. So this is what it's going to look like from Northumberland. Now, the further north you are, the more of the sun the moon will cover. Okay, so even going to like Scotland, you'll get slightly more of the sun covered. If you go further south, slightly less covered. It's about 30% of the sun covered by the moon in the middle of the eclipse, 30% of the area of the sun. So it started just after 10, well, just 10 past 10 on June the 10th. It's a Thursday. I've booked time off work for this. Mid-eclipse, 11:18. Eclipse ends 12:32. That should be PM, obviously, PM. So it lasts for about 2.5 hours. Now, I don't know if anybody here is equipped to view the eclipse. That may be something you can try to fix in the time between now and June the 10th. And I'll try to give you a little bit of a guidance for how to do this. The depressing thing about this is that in the past, since the year 2000, June the 10th was cloudy 81% of the time. So there's like a 1 in 5 chance historically that we'll see this. Okay, 1 in 5. Let's see. Now, to observe the eclipse, if you go with the telescope, it needs to be filtered. So if you're already set up for like solar observing, you'll already have the filters that you need. So there's a variety of ways you can do this. So the thing in the picture is, I don't know if you can see this. I can't see myself on the screen at the minute. So let me have a look. There it is. So this is something I got with my telescope, so I didn't have to buy it, but you can see there's like an aperture in it where it looks like a mirror, but it's actually a filter, and it just attenuates the sunlight by about a factor of 100,000. So you're looking at an orange version of the sun through there. So my 8-inch telescope becomes effectively a 2-inch telescope. So it's not great resolution, this filter, so I wasn't happy kind of like using it. You can make your own filters using kind of like filter paper. So if you're prepared to shell out 18 to 20 pounds, you can send away for a sheet of A4 of this stuff from lots of different vendors, and you can just cut out something which fits your own telescope. I'll show you how naff mine was when I first made one. Look at that. Look at that. That is rubbish, isn't it? That's terrible. And I made it to fit the Society's Skywatcher refractor. So it kind of, it's not this one, the other one, the one that's in the observatory, it fits on there. So it goes over the end so that you've got it on the end of your telescope like that. Okay. I made a slightly better one. I bought some more Bada filter a few months ago, and I've got another filter for the 8-inch, which makes more use of the aperture. So I'm hopefully prepared for that. Now, low-tech solutions. I've tried this before and it works, okay? You can make a pinhole projector, and you can do it as simply as taking a sheet of A4 card or paper and just putting a tiny, tiny little hole in the middle of it, okay? And if you project that kind of like hole onto another sheet of paper or a wall or something, you'll get a tiny image of the sun, okay? If you make it too big, it will be too blurry and you won't see the bite out of the sun. If you make it too small, you'll get a sharper image, but it might not be bright enough for you to see much, okay? So it might be worth experimenting. I mean, it's like a sheet of paper. You can put multiple holes in it, you know? It'll work. In fact, you can get quite creative with it. If you've got a colander, you can do art. Okay. So, I mean, literally anything with a hole in it will work. So, you know, get creative with this. I've got eclipse glasses. So, I mean, there you go. So these work. I mean, they're literally, you can't see anything through them. So if I put them on there, you can't see anything, but it lets you see the sun. So I was trying them out before, and you can see the sun quite easily. So you can still order those. That's a cheap solution as well. The eclipse will look great through those. So, you know, there are various low-tech solutions. If you don't have a telescope or binoculars, you can still observe this eclipse. In astronomy books, I used to see recommended pointing your telescope at the sun and projecting the image onto card. And I really don't recommend doing that, because if your telescope is of a decent size, you could create a fire inside your telescope, like I did one year when I was trying to capture Venus near inferior conjunction. I had my telescope pointed in the vicinity of the sun. This is the 8-inch telescope. And I went round to see how much, you know, how close the sun was to shining on anything, and there was smoke inside the telescope. So I mean, you know, don't try this with the telescope. It's better with the filter. Only do it if you've got a really cheap telescope that you don't mind damaging, okay? And who has that anyway? Right, okay. Now, before I get onto the deep sky stuff, I'll make this offer, okay? I know we've got like COVID and all the rest of it. I've got stuff here. I'm prepared. If you've got no way of observing this, if you want to contact me privately and you want to pop around for like 10, 15 minutes, half an hour and observe the eclipse with me, I've got various things around here to allow you to do that, okay? So if you feel like you really want to see it, but you've got no way of seeing it, you can contact me and we can sort something out. I've got a big back garden. We'll do everything socially distanced and we'll keep the numbers down. Okay. So there's an offer there if you can't do it. I'm in red row, if that helps. Right. In the chat. Filter or block for your finder scope. Yeah, I generally take my finder scope off when I do this. I'm just looking. Thin cloud can help. Also, why bother with the telescope? Just a filtered camera. Yeah. As long as everything's kind of protected. Do you know what? There was an eclipse in 2014, and it was cloudy. It was like high cloud, and it was just on the border of kind of being. Because if there's cloud there, it really messes your filter up. Because if the sun isn't bright enough to shine through the filter, but it's too bright to look at, that's really horrible. And that was the case almost for that eclipse. Sometimes the cloud can be thin enough for you to get away with your camera without a filter, but that's dangerous. And you definitely don't want to be looking at the sun in case the cloud suddenly breaks or it's thinner. So it can be really dangerous. Take no risks. It's not worth it for just like a partial eclipse. Right, into the deep sky. So, you know, it's not enough to see anything like there is in that picture, okay? So the Milky Way vanishes from Northumberland skies. In the summer, you can't see emission nebulas unless you're using like filters, but even then I would imagine it's difficult. So I'm going to just draw your attention to some of the brighter things that you can see, which typically are the star clusters. So globular clusters are brilliant at this time of the year. So I'll just illustrate a little bit about those globular clusters. They're the things you can still see with telescopes and binoculars. Okay, so this is a depiction of tonight, about 11:30 p.m. The moon's about to come up in the southeast, and we're looking at a twilight sky, and the stars are out. You've got Arcturus high in the south, and you've got Vega, Altair, and Deneb just out of the picture, making the summer triangle towards the east. If I add some of the constellation lines, maybe that helps a little bit. The things that I'm going to encourage you to look for if you want to do any deep sky stuff are the globular clusters. There happen to be loads of them at this time of the year. Okay, so if I put on the brightest globular clusters, you can see there's quite a lot to choose from. So these are visible all the way through the summer, even if the background sky is a little bit brighter than usual. So M13 up in Hercules is the great Hercules globular cluster. All of the others are pretty bright as well. Okay, so they're all worth tracking down. The majority are Messier numbers. There's a couple of Caldwells and NGCs mixed in there as well. But you can see they're kind of in this part of the sky. If I was to rotate around and look towards the east more or the north more, there would be very few. Globular clusters congregate on one side of the sky. And there's a reason for that. Now, globular clusters look like this. This is a picture of Messier 13 taken through a telescope. They're broadly spherical, okay? So they're balls of stars and they contain hundreds of thousands. And the biggest globular cluster, which in fact might be the nucleus of a galaxy cannibalized by the Milky Way, is Omega Centauri, contains around 10 million stars. But they're kind of roughly the same shape. And the stars within them tend to be like the sun or even lower mass. They're pretty small, yellow, and they're very, very old. These clusters are almost as old as the Milky Way itself. They're formed alongside it, and they're formed around it in a great halo. And these things orbit around the galaxy over periods of billions of years they take to go around the galaxy. And when astronomers began to map these things, so which part of the sky they're in, how far away are they, it turns out that they're kind of uniformly distributed around a particular point, and that point is not where we are, not where the sun is. So it was one of the key pieces of evidence that the sun is not in the middle of the Milky Way, and we got that evidence back at the start of the 20th century. Now, before I just briefly show you what that is, I'll just show you some more examples. They kind of look, some of them are more compact than others. In some of these, you get black holes, we think, in the center, and the black holes kind of adjust the orbits of the stars to pull them more tightly. and you get a higher condensation of stars in the center. Some of them don't seem to have that. Some of them are more loose in appearance. But anyway, this is M5. M5 is as good as M13. I don't know if you knew this. Everybody looking for globular clusters tends to go to M13, okay? But M5, for us northerners, is one of the better clusters in the sky as well. I think it's slightly brighter than M13. M12 is a little bit dimmer. Just outside of the frame is M10. There's actually quite a lot of globular clusters scattered around this part of the sky. Here's some more, just to kind of like show you how they vary. M71 was originally classified as an open cluster, so something like the Pleiades at a great distance. They thought it was a different type of cluster, but it's actually a globular cluster in a very rich part of the Milky Way, seen against a very starry background. M92 is the other big globular in Hercules, not that far north of M13. But you get the idea. They're just hundreds of thousands of stars within these things. And through a telescope, you can begin to resolve the outer regions of these into just countless stars. The bigger the telescope, the better when it comes to observing these things. Now, if you plot them, okay, now what I've got here is a map of the globular clusters, kind of in 3D, but sort of in the picture you can't see it, but it's kind of like the galaxy would be here. Here's the bulge in the middle. If I just draw it in, this would be like the bulge, and we're looking at the galaxy edgeways on. So it's kind of like that. Okay, that's the perspective we're looking at this from. So the globular clusters are scattered around the galaxy in all directions. But the center of kind of like the distribution is the center of the Milky Way, okay? And the sun is nowhere near the center of the distribution. So if you think about it, if you divide your sky into two, okay, so maybe this is like looking towards the south, maybe this is looking towards the north, you can see that if you look towards the northern sky, there are very few globular clusters. But if you look towards the southern sky, they're all there. And actually, they're all in the direction of the center of the Milky Way, which is why at this time of the year, when you're looking out into the sky, the Milky Way basically comes down in this direction. This is the Milky Way between those lines, and all of the globular clusters are in there as well. Okay, so you're looking at key evidence that we're not in the center of the Milky Way when you see that. So there we have a slightly better rendition of that. Okay, so globular clusters are fine to look at even in these very twilight skies of the Northumberland summer. Right, now just looking further ahead, Jupiter and Saturn are coming. You can see Jupiter and Saturn in the morning sky about a couple of hours before sunrise, but who's up at that time at the moment? Sunrise is what, 5 a.m. at the moment? So you need to be up at 3. You can actually see Jupiter in broad daylight. So if you're able to find it in broad daylight, you'll be able to observe it and image it as well. The Perseid meteor shower obviously is coming in August, and the Milky Way will be back to full glory between August and October. Okay, so that's the best time to see it from the UK. Right, that's it. So that's a brief tour, I guess, of summer astronomy in Northumberland. So